Let's prove it. Hope you guys are all done writing that down. So proof. Actually, before we do that, it's always good in a contradiction proof to write down the negation. I'm not going to be a stickler about it, but it's good to write it down so you don't make a mistake. So negation of this. So remember, to negate a for all, you do there exists a P in our set of primes such that there exists a in our set of natural numbers such that the negation of P divides A and P does not divide A. P divides A implies P not divide A plus 1, which is equivalent to there exists a P in primes such that there exists an A in the natural numbers, such that the opposite of this is P divides A and P does not divide A plus 1, which means P divides A plus 1. And by the way, I should say, because I've seen a couple mistakes in homework, that some people, sometimes might be weird, because P divides A plus 1, what does that mean? Does that mean P divides parentheses A plus 1? Or does that mean you're doing P divides A plus 1? And the answer is definitely this, because everyone listening, both now and in the future, think to yourself, what does this mean? P divides A is a statement. It's either true or false. It's just a thing saying true or false. So how do you add 1 to it? That's kind of like saying, I own a Ferrari plus 1. What does that even mean? You know what I mean? Like you can't add 1 to a statement. It doesn't really mean anything. So P divides A is definitely not A divided by P. They're very different things. And in fact, I couldn't even use, technically this is the wrong sign to use, because this is between numbers and P divides A is not even a number. And I also can't use the equivalency sign because A over P is not a statement. So I don't even know how to, they're so different. I don't even know how to express correctly that they're not the same. But anyway, it's apples and oranges at the point. So yeah, so this is what we're trying to prove, this is the negation. We're trying to prove this lemma. So proof. So we're doing a proof by contradiction because we kind of thought that's the only way we could really do it. Proof by contradiction. And we're going to assume, for sake of contradiction, that there exists there exists a prime P and an integer A such that P divides A and P divides A plus 1. That's exactly what the negation says. We assume the negation. Now we want to show this logically leads to something ridiculous. Logically leads to a contradiction. And since contradictions can't happen, that means our assumption must be wrong. And if our assumption that the negation's true is wrong, well, that means the opposite of negation, otherwise known as the original statement, must be true. So how'd the proof go? So knowing that P divides A and P divides A plus 1, the next natural step is to just say what that means. Thus, by definition of divides, there exists an integer k such that pk1 equals A, and there exists an integer p2 such that, or not p2, k2, such that pk2 equals A. Equals A plus 1. That all makes sense. Then consider the difference. Consider a plus 1 minus a. A plus 1 minus a equals pk2 minus pk1 by substitution. But then the left side, that's going to equal a minus a, which is 1. And then we can factor this side, pk2 minus k1 by evaluation and factoring. Technically, you should probably do this in 2 steps, but it doesn't really matter. I'm just saving some time. Note, so now we're almost done, right? Because once we show that p divides 1, once you show that p divides 1, we're basically done. But to show that, we have that little step. We have to make sure that k2 minus k1 is an integer. Because, I mean, technically, every number can be multiplied by something to get 1. For example, 3 times, or like 4 times 0.25 equals 1. But 4 does not divide 1 because 0.25 is not an integer. It's really important we make sure that our k2 minus k1 here, the thing we're multiplying by p, is in fact an integer. So note that k2 and k1 are in Z, and the integers are closed under subtraction. So p divides 1. And that should be a red flag. Uh-oh, this does not look right. Something went terribly, terribly wrong. Further, p equals 1 times p. And p is in Z, since p is prime and primes are integers, specifically positive integers. The point is, though, by definition, one divides p. Then, by theorem, since 1 divides p and p divides 1, p equals 1. That's where you use this beautiful red theorem here that I proved like weeks ago. All comes back together. That's why you do these things in math, because it will be useful in the future. So 1 divides p and p divides 1. Well, I guess you could argue then, if you just prove everything in math would be useful in the future, it's a giant circle of uselessness. But it's amazing and fun, and also really important to like coding theory, cryptography, physics, and all that. So I guess there's your point if you need it. If you need a point other than fun. But, sorry, I got sidetracked. So p equals 1. Why is that an issue? Contradiction. P at the very beginning is a prime. So p is greater than 1 in our definition of prime. So there's our contradiction. And then the last thing I would add after that is one little sentence just saying, thus, our assumption is false. Therefore, for all pre-prime and for all integers a, p divides a implies p does not divide a plus 1. Just a nice tie everything together. Any questions on this?
Is there a formal definition for prime? Did we do that?
Yes.
I don't remember.
You're good. A prime, by definition, is for all p in the natural numbers. You could do the integers here, doesn't matter. We'll see why in a second. P prime, if and only if, this makes a definition, we have an if and only if. P prime if and only if P is bigger than 1 and for all A, or maybe I'll say for all D in the natural numbers. Wait, let me start it like here. I'll say P prime, if and only if I put that over down here, that is P is greater than 1 and for all D and N, P divides D implies, I'm sorry, D divides P implies D equals 1 or D equals P. Basically saying you're greater than 1, and if any natural number divides you, the natural number is either 1 or itself. So that's why P equaling 1 can't happen, because we assume P is greater than 1. Technically, I don't really see why you really need this P is greater than 1 thing, because even if you got rid of this, 1 wouldn't be prime. Well, actually, no, yeah. I guess if you got rid of this, 1 would be prime, and we don't want 1 to be prime. The reason we don't want 1 to be prime is because of the fundamental theorem of arithmetic, where we say you can break everything down to the atoms, right? Where you say like, oh, okay, 15 equals 3 times 5. Or, you know, let's say 12 equals 3 times 2 times 2. But the problem is if 1 was a prime, well then why not do that? Or that, or that, or that, or that, or that, or that, right? If 1 was a prime, then there would be non-unique ways to write integers as sums of prime, as products of primes. And really, that's almost, in a weird way, that's almost a more pertinent property of primes, is the fact that they're the atoms of arithmetic, rather than the fact that they're only divisible by themselves or 1. They're very related, but also kind of different. It's a very weird thing. I'll be happy to talk about it later, but we gotta move on. That makes sense though, Herman? Good.